discussing an essay that we just published on Substack, and it's the title is "The Art of Science Engineering." And the idea here is that we have, on the one hand, we have two industries where, interestingly enough, they have an inverse problem. One is life sciences. Life sciences is an industry with highly educated artisans that requires more of an engineering approach. In other words, we need more engineers and less artisans in life sciences. And in industry, I take the car industry as an example, but you can use other, aerospace, machines, similar. In industry, we have the inverse problem where we have a lot of engineers and we need more artisans. And the essay goes along the lines of some conversations that I had and some talks that I've listened to, Jensen Huang and Vijay Pandey and Alan Asparuh-Guzink. I'm going to discuss them in detail. The idea here is that in life sciences, we need more engineers. So all the three talks, Alan, Jensen, and Vijay, they are coming from the life sciences perspective. And they obviously are different perspectives. One is a VC, one is a CEO of a large tech company, and one is a professor. So, but they all come from the same angle. They're saying we have lots of artisans and lots of good chemistry and physics and life science and all of that stuff in chemistry, in biology. We've come pretty far. We have, medicines, we have penicillin, we have vaccines, we have all those things. But to get us to the next level, if we really want to have the 21st century as the century of biology, we need to start thinking more along the lines of engineering. And I added, this is now my personal view on the situation in industry, and I'm taking Tesla as an example, where we have actually too much engineering in industry, and that goes back to Henry Ford and the assembly line. And we need more artisans there, and I'm going to elaborate on that. This is not even on podcast. It's February 14, 2024. This is Crimdelco. Since the last update, we're down 3.8%. The market's down 1.5%. For the year, we are down 18.9%. The market is up 4%. We're underperforming by 22.9%. So let's talk first life sciences. Then I'm going to go over to industry, and then I'm going to try to do a synthesis here. The idea here is really what is the future of work within two large industries. You can probably extrapolate this to other industries, finance, and so on. But let's just, for simplicity, focus on life sciences and on industry. So life sciences needs more engineers. Let's start with Alan Asparuh-Guzink. Like, he's a professor he has a couple of chairs at the University of Toronto. He's a pretty interesting personality. He's a theoretical chemist. He's a computer scientist. He's I think he has a chair for material science. So, and it makes a lot of sense why he has those chairs, because he is trying to do what sort of we dream of here at Orange Capital Partners, which is we want to accelerate physics. We want to accelerate atoms. We want to bring Moore's law into the world of atoms. So this is what he's trying to do in his realm. We're obviously trying to invest along those lines. The idea is that, look, you had 250 years, probably even more, but let's say 250 years of pretty successful handling nature. It was called alchemy, then it was called chemistry, and then physics, and then physical chemistry and quantum chemistry, and it just got different names as it progressed. And it progressed in a good way. And we have a lot of things. Look, we can argue about whether science is prolific, whether we're wasting too much money, whether government is involved too much, and all that stuff. But in the end, if we compare ourselves today with 50 years ago, 100 years ago, we obviously have made a lot of progress in material science, chemistry, and life sciences. Whether it's we have all different kinds of materials and plastics, and we can go to Mars, we can go deep sea, we can drill for oil, we can we have materials that can handle thin layers, that you can go ski at minus 20 degrees, all that kind of stuff. So material science, let's call it material science. Okay, let's call it life science, because it's really about how to handle nature. And what you can do with nature is you can keep, structuring it and then try and error yourself to some sort of result, which is how the industry is working today. Or you can start applying more computational methods. What I mean with that is that you do what's being done in other areas, particularly in, let's say, machine learning, Gen AI, all these fields have shown us that if we train models, if we design proper algorithms, train them properly, and feed them with the right data, we can get a lot more intelligence out of these things. And the question now is, can we do the same thing with nature? And Alan, in his talk, that I'm going to put everything on the show notes, so let's not get boggled down in details here. One of his talks recently talks about this, and he talks about two things. He wants a robot lab, and he wants reproducibility. And I think this is the key. Reproducibility is the key. And the reason it's important is not just for science, of course. It's also important because once you have reproducibility, you can start building an assembly line. You can start engineering your way through problems into better progress. This is actually what happened to industry. This is what Henry Ford did. Henry Ford introduced the assembly line into industry. That was his biggest achievement. And I believe that Elon Musk is trying to do the same thing. He's trying to use computational methods and sort of the idea of the assembly line accelerated with Moore's law into the production method of, let's say, Tesla. This is the idea. I'm going to get back to Tesla in a second, but let's stay with life science for a second. Then we have Jensen Huang. I spoke about his talk that he gave at JP Morgan 24, where he spoke about in silico design. It's a very similar topic. Okay, we have these designers of molecules and drugs. Jensen was talking about drug discovery, but we could apply the same thing to material science. So we're trying to sort of in a bespoke method in the lab. We're trying to design certain things, proteins or inhibitors or whatever it is, targets. He's making fun of the nomenclature, but that's a different story. Like, think about it this way. Like, what if you had a more automated, more iterative, more computational way to go through millions or billions of iterations? What if you could do something like AlphaGo Zero does when it plays Go, and do sort of a Monte Carlo search while trying to assess the next action, right? Whether it's a moving Go or whether it's which Petri glass should I now use with which molecule to do what? Like, think about it. Like, it's the same problem, right? You could kind of look at science as a game. And say, look, this is a game that can be tackled by computers as much as Go can be tackled by computers. Yes, it's more complex. The domain is more complex and all that stuff. We get it. But that's why we have to start thinking differently. And this is a lot more profound than just saying, oh, we need to use more machine learning in life sciences, because this is not what it's about, okay? This episode today is about culture. It's about people. It's about how to think about your job, how to think about your industry. What are your thoughts when you actually go to university and study chemistry? Are you thinking that you're going to be a data scientist, or are you thinking that you're going to be sort of an in silico designer, or are you thinking that you're going to just walk around like a sort of a lab rat with lab goggles and stuff? My son the other day told me that one of his friends comes to school. He's going to high school with goggles, lab goggles, and I think what this child is really signaling is, look, I want to be in the lab. I like this kind of work. And I have bad news for him, because I don't think that the future of lab work is going to be goggles and white coats. The future of lab work is going to be on the screen. Whether you need to understand C++ or prompt engineering or whatever, that's not the point here. Okay, what I'm saying is you're going to go out of the lab, and this is very interesting. In Jensen's talk, he compares the chip design world to life sciences. He said when I started in the chip design world in the 1980s, he said I was the first generation that did not go to the lab anymore, because we did in silico design almost exclusively. And he said, I think the same is going to happen to your industry. So really, really important. And again, like if you take, let's say, a classic reinforcement learning problem, right? And or a reinforcement learning algorithm, whether it's, on policy, off policy, offline, online, all of that stuff. In the end, what is reinforcement learning, right? Reinforcement learning is some kind of mixture of supervised learning where you're fitting a value function. You're trying to somehow figure out, okay, in the state where I am right now, in this, on this particular uh, position on the Go board or chess board, from now on, this is kind of an average expected value that I can, expect a reward from this particular position. And then you're adding a certain action to that, the nomenclature would be Q learning here. So you're fitting a Q function, which says, okay, given the next action, what is my advantage? So if I do this action versus that action, given the value function so I am in this particular coordinate, from here I can expect 150 of reward. Okay, if I make a move now, I have, let's say, 5 different options to move. Each one gives me a different type of relative value against the sort of baseline, which is that value 150. And then I'm going to choose the one which gives me the most. So if you think about it that way, this is, of course, being applied to chess or Go, but why not being applied to science? Why not being applied to material science? If I dope this particular chemistry with a little bit more nickel, then my expected sort of future value of the whole process, the trajectory is higher than if I dope it with a bit less nickel or whatever. Like I hope this comes across, which is kind of a stupid way to say, do you know what I mean? But the key here is really, in the end, what we're trying to achieve here is we're trying to build a system, a workflow that allows us to iterate much faster at a lower cost of error. This is what it's really all about. And the life science conversation, I want to finish the life science conversation with Vijay Pandey. There's always somebody I listen to. I would say, I don't know if he's listening to this, but yeah, I think Vijay, you need to go out there, but you need to make your hands dirty. Like you sound like a parrot at this point. And the only good thing is you're a parrot of yourself 5 years ago. Like there's nothing new here. You're talking about shoulds and oughts and this and that, but in the end, life science is shackled by the FDA and approval processes and all that stuff. But like we need, he's talking about go to market. Yes, we need new go to market strategies, but in the end, is that really what it's all about? I don't know. So anyway, but that's just a tangent. It doesn't matter. But what he's talking about more importantly is he is a big fan of the idea that we need a cultural shift from bespoke to engineering. And I want to leave it at that. Maybe Andreessen Horowitz has the kind of clout to actually do that, build startups that can do that. But we have burned our hands with computational biology, gene editing, and all of those things. There's tremendous amount of talent, tremendous amount of intelligence out there. The problem with, in my opinion, the problem with biotech right now is cultural and only cultural. The science is there, the problems are there, but if you have companies like whether it's Beam, whether it's CRISPR, whether it's Twist, whether it's whatever, and the founders are professors and they are sitting on the boards, and even worse, sometimes even the chief technology officer is still a professor somewhere, and all of that. Not you can make some money, but this is not $100 billion industry. And I think that's the problem that Vijay Pandey is up against. I'm sure he knows it. He's been a professor himself. To move these people out of the ivory tower into industry and make them productive is unbelievably hard. And I want to use this as a transition now to Tesla, because this is exactly what Elon Musk has been able to do. And I think he's stalling a bit now on the AI front. He's stalling because he's not able to bring enough talent from the ivory tower or from, proxy ivory towers such as Google or Meta into industry. What we need in industry is the exact opposite. What we need in industry is less engineers and more artists. And that's the title of the essay, okay? The art of science engineering. It's both, okay? The assembly line that Henry Ford introduced was useful in the 1910s. I think it's outdated today. We can't just do, process engineering. Like if you go to an average business school or even a top business school and you learn, organizational design, engineering, whatever it is, all these kind of classes. If you go to an engineering school that looks at it from an engineering perspective, it's all the same thing, which is, okay, what is the pattern? What is the reproducibility? What is the workflow? And then let's just scale it up. And that helps to scale. I mean, that we've been able, Toyota has been able to build, millions of cars and all of that stuff. But that's not the future, because what we want to build is intelligent electric cars. We want to build intelligent machines. We want to build, distributed bottom-up energy systems. For that, we can't just have a bunch of engineers designing something and then reproduce it a million times. We need more artisans. We need artisan engineers. We need the art of science engineering, whatever nomenclature you want to use. I hope this idea comes across, that what we really need here fundamentally is people that can solve problems on the fly, that can this is okay. Let me jump to my conclusion. I think this is going to make it a bit easier. I think the solution actually is a lot more simple than you might think. All you have to do as an entrepreneur is just introduce iteration into your workflow. It's all about iteration. And I want to add to that the way you iterate across the value chain in the 21st century, it's going to be sort of upside down, in a sense that you start with the end product and then you go back and you think about, okay, what kind of data do you need? Whether it's data, the typical data, like, let's say, if Tesla wants to build a self-driving car, it needs a certain amount of data to train that car. So that kind of data. But it's more than that. It's data. Let's say, what kind of engineers do I need? How am I going to do a proper search for this role? Because this is what the role is going to, the goal of the role is going to be X. And to fill this role properly, I need Y and Z and so on and so forth. So everything is always, it starts with the end product. This is something that, companies like Amazon have revolutionized. You start with the goal. Okay, what is it I'm trying to achieve? And then you work backwards. And I think this is a lot more subtle than just, again, this is, let's say with the Tesla full self-drive stack, you can say, okay, that makes a lot of sense, right? You start with, I want this car to be able to drive itself. And then you go backwards and you try to understand, okay, what kind of data do I need to train a car end to end? What kind of data management? What kind of, do I need Dojo? Do I need, like, it makes sense on that front. But this whole idea of building a stack is, it applies to the whole company. It applies to, this is the future of work. And the future of work is the future of entrepreneurship. Because this is what successful entrepreneurs ought to do to be successful. I mean, if your approach is, the reason companies like BMW or Toyota cannot compete with the future startup, whether it's Tesla or even the next company that is going to revolutionize the car industry, the reason is simply, this is the innovator's dilemma again and again and again. It's because they are stuck in their ways. It's not because they're stupid. It's not because they're lazy. They are stuck in their ways, literally. Read The Innovator's Dilemma, Clayton Christensen. It's the Bible. The reason it's the Bible is because it's applied in a general way. It has all the answers to all the big questions in business. Why is BMW selling electric cars that start at $100,000 versus a Tesla that costs $45,000. Why are they doing that? Why am I hearing from my friends that they prefer a BMW because it's more luxury? What are they doing? They're going up the value chain because they can't compete on cost with Tesla. And the reason they can't compete on cost with Tesla is because Tesla is iterating. It has at least the first initial signs of an artisan engineer in its ranks. It hires people that think like that. It works like that. It produces like that. It's a very different way of producing the same product, which is a car. And the reason the car is very different is, first and foremost, it's the cost. But it's not just the cost, of course. It's the value that you get. Because what you're getting with Tesla is a car for $45,000 that BMW, if they had to make the same car, would have to charge probably $70,000 for it. And they're charging $100,000 because they're adding a few leather seats and this and that Tesla doesn't have, but that's okay. So my point here is that the future of work is the future of entrepreneurship, and it's going to be about how to build artisan engineers. And the way you're going to do that as an entrepreneur, as an investor, is by channeling capital towards situations that have high iteration embedded in the workflow. What that requires, and there's a couple of things that we talk about in the essay, which I think are important, it requires a new approach towards some of the big milestones that every company or everybody's career has. For example, failure, success, promotion. You see, it's easy to say, well, we just want to iterate more, right? But how can you iterate in a company like BMW when, let's say, you come up with something that doesn't work well, you're going to be considered a bad engineer. So what you're going to do then is only make things where the probability of success is incredibly high. That is very difficult to iterate in a situation like that. So what you need is, you need to reformulate the failure. For example, what is failure in engineering? It's when you're not able to explain why something is not working. That's failure. Like, malfunctioning things. Like mistakes are a feature, not a bug. And the question is not how to avoid mistakes. The question is how to quickly correct them at low cost. And you need to be able to explain why they happen in order to correct them. So that kind of switch of mindset, that's the future of work. That's the future of entrepreneurship. That's the future of industry. I think to summarize this essay, it's kind of crossing two big themes. One is a more simple idea, which is just we need more engineers in life science, and we need more artisans in industry. So that's one thing, and I think it's a nice sort of inverse problem, interesting, makes a good essay. The other thing is it's a little bit more subtle here. It's the future of work in general. The future of work, and this applies not just to investors who are, deploying capital to companies. The question of the future of work, applies to everybody. In fact, it applies to you. In particular, if you have kids that are maybe teenagers or things like that. Because for them, the question is, okay, what is my future going to look like? And let me tell you something about your future or your kids' future. It's going to have to be exactly the same way. You have to be able to be an artisan engineer. You have to understand how to fail fast at low cost, understand errors. Your whole raison d'etre, you wake up in the morning because what you want to do is understand why something is going to fail. Look at SpaceX. They launch these rockets knowing they're going to blow up, but they set some goals, right? It's not just try and error like randomly, of course. You set some goals. You say, okay, if this rocket goes to orbit, this is the type of data we can get. And if it keeps going further, it's fine. We're going to collect some more data, but that's fine. And then if it gets to orbit, mission accomplished. It blows up, it's fine. If it blows up before, then the question is, okay, why did it happen? In the book, Liftoff, one of the things I noticed about Musk is he's very, very peculiar about mistakes. It comes across as challenging, and I think that's why he has this reputation of being so hard to work for. It's not because he's an evil person. I don't think so. I think it's because he's incredibly picky about, okay, there a mistake was made, something went wrong. What is the mistake? Explain it to me. Give me the reason, because I need to understand what went wrong so I can fix it. That's what the nature of iteration is all about. And this type of, mindset, this type of attitude, I think it has to go all the way down to the university, to the way people are educated, particularly in science. Now, this is for another episode, of course, how science and academia can be reshaped to produce better future entrepreneurs and engineers, artisan engineers that can build those industries. By the way, there's a lot of industries that need to be built. Okay, it's healthcare, it's defense, it's academia, education itself. There's a lot of industries that still don't have any of that, and the only industry where this is being applied right now is the digital industry. The Facebooks of this world and the Googles, and they are the most valuable companies in the world. But we can transcend this. We can get into atoms and have Moore's law applied to atoms. But for that, we also need a cultural change. A cultural change, Silicon Valley has to penetrate all these other industries. And the way it's going to do this is through entrepreneurs like Elon Musk and future entrepreneurs that can do that. That can transcend hierarchies, that can change nomenclature, a failure is not when your machine doesn't work. A failure is if you can't explain to me why it doesn't work. Thank you.